This video is going to talk about Proposition 6.1 from Section 6 on incidence geometries in your textbook. Okay, so a reminder, what do you need before we talk about Proposition 6.1? So far, the assumption is we are going to be working in an incidence geometry. So remember, a geometry is a collection of points together with a collection of lines, where the lines are built from some subset of the points in your geometry. The incidence axioms go as follows. You have the first incidence axiom says pick any 2 points in your geometry. There's a unique line that contains those 2 points. Second incidence axiom, pick any line in your geometry. The line has at least 2 points. So those two are the reverse of each other. And in any incidence geometry, you do have 3 points that you can find that are not all on the same line. Maybe there's lots of groupings of 3 points that's true. Maybe there's only exactly one group of 3 points where that is true. Okay? So, going from that starting point, let us now look at Proposition 6.1. So Proposition 6.1 says, in an incidence geometry, any 2 distinct lines, so remember what distinct means, it means 2 different lines, can have at most 1 point in common. Please note what this means. This means that your 2 lines can either intersect or not. So notice here those would be 2 picture illustrations of the situations. The case where the 2 distinct lines intersect, the case where the 2 distinct lines do not intersect. Please notice these 2 examples are drawn in the same geometry that Euclid defined, where you're on a flat piece of paper. Now, so notice what this really means. So you've got these 2 distinct lines, and it means they have at most 1 point in common. So what it's actually doing is it's excluding the situation where you've got your 2 lines and they actually intersect in more than 1 point. Now, if you intersect in more than 1 point, or you meet in more than 1 point, or you have more than 1 point in common, you definitely have 2 points in common. If you have 4 points in common, you definitely have 2 of those 4 points are also in common. So what we're going to do to show why this Proposition 6.1 is true, we're actually going to go through the proof of it. But we're going to go through the proof of this proposition by showing there's no possible way that you could actually have 2 points in common if you have 2 distinct lines. Okay? And notice what that means. If you can't have 2 points in common, it automatically excludes more than 2 points in common as well, and that leaves you with simply the case of exactly 1 point in common between the 2 lines, so 1 intersection, or exactly no points in common. Okay? So let's look to see what we want to do here. First thing we're going to do is this proof by contrapositive. So that is let's assume we actually do have 2 points in common. Okay? So what we're going to have is we're going to start off and we look at some incidence geometry. We don't yet jump to a model, so we don't establish which geometry we're in. The only assumption is that we're in an incidence geometry. Notice what this means in terms of citations. This means the only thing we're allowed to use so far is the 3 incidence axioms. So, we look at our incidence geometry, we go ahead and we name L and M to be 2 lines that we would like to pick out of that geometry. And what we're going to do is we're going to go ahead and assume that they have 2 points in common, and we'll go ahead and call those 2 points point A and B, where the points A and B are not the same point. Okay? In other words, we're looking at this situation of the picture down at the bottom of the screen there, where you've got 2 lines and they share 2 points in common. Maybe more than 2 points, that's fine, but we're just focusing on they definitely have the 2 points A and B in common, where A and B are 2 different points. Now, this is where we go and apply axiom 1. So we go back to our incidence axiom number 1, and we say, all right, well, if you've got the 2 points A and B, what do we know from incidence axiom number 1? We can find a unique line, that means exactly 1 line, that contains both of those 2 points. Well, notice what does that immediately tell us? If there's exactly 1 unique line that contains both the points A and B, that means you can't actually have line L and M to be 2 different points, and that gives you immediately that L and M are in fact the same line. Notice we come back up here And what does that tell us? We took the negation of at most 1 point in common. We grabbed 2 or more points in common. And then we got the negation of the beginning right here of distinct lines. We got 2 lines that were really exactly the same. So what we just did is a proof by contrapositive. We took the contrapositive statement, we proved it, and logically speaking, your contrapositive statement and your original statement are exactly the same, which means this proposition 6.1 is true. Notice also it is simply a rewriting or an application of that very first incidence axiom. And this is a proposition that gets used all the time.